This is the beginning of lecture note 7. We're going to talk about hypothesis tests and confidence intervals for multiple regression. Why do we care about this? Hypothesis tests, and just like in the single variable case, we want to know, can we reject null hypotheses about the coefficients in our multiple regression? We will also do joint hypothesis tests on multiple coefficients. In other words, maybe does beta 1 and beta 2 simultaneously equal 0? This is going to help us select different models. It's going to help us decide which variables to include in models. So let's write down a couple of examples. So what's the t-stat in this confidence interval for one of the coefficients in a multiple regression? Suppose we have the following model. yi equals beta 0 plus beta 1, x1i plus beta 2 x2i plus, let's go out to beta k xki plus ui. So we have k coefficients, or k variables and k coefficients. Let's focus on maybe the second one. So let's write down some tests for the coefficient beta 2. So here's our population model. Let's suppose we've estimated it in R. We get a coefficient estimate for beta 2 hat. So we estimate the model in R. And get coefficient estimate for beta 2 hat. And of course, if you have an estimate of beta 2 hat, you will get estimate of standard error of beta 2 hat. So we get we need, in order to perform our confidence interval or our test, we need to also know the standard error of our coefficient. So just like in the single variable case, because of the central limit theorem, if all of our assumptions hold, our t-stat has a normal distribution. So our t-stat is equal to beta hat 2 minus our hypothesis about beta hat 2. So let's say, let me back up a bit. Let's say our hypothesis about beta hat 2 is a null hypothesis that beta hat 2 is equal to 0. Actually, this should be beta 2 equal to 0 versus an alternative hypothesis that beta 2 does not equal 0. Cool. So that's our hypothesis. We're going to specify some tests that will allow us to reject or fail to reject this null hypothesis. So the t-stat is unchanged. It's equal to beta hat k minus, well, let's do for 2, beta hat 2 minus 0, because our null hypothesis is 0, over the standard error of beta hat 2. That's our t-stat. And what's our rejection rule? This is our 95% confidence rejection rule. Whoops. Rejection rule. Reject if the t-stat in absolute value is greater than 1.96. Okay, so just as before, nothing's changed here except we are looking at the coefficient of x2, beta hat 2. So before, in our single variable model, we were only considering beta 1, now we're considering beta 2 and beta k, etc. So the t-stat is not changed. That's great. The confidence interval is not changed, so the 95% confidence interval. 95% confidence interval is beta hat 2 plus or minus 1.96 times the standard error of beta hat 2. The p-value also has not changed, so we can write down the p-value from before. Equals 2, 5, means go look it up on the z-table of the negative of the t-stat, absolute value of the t-stat. So the nice thing is we can apply, as long as the assumptions hold, the least squares assumptions, then we can apply the same tests as we had before in the single variable model. Let's do an example of class size and test scores, our favorite example for this class. Let's do it in blue. All right, so we're going to have two models, one with a single regressor and one with two regressors. All right, model 1, test score equals 698.8 with a standard error of 10.4 minus 2.28 times student-teacher ratios with standard error of 0.52. Model 2, we have two regressors in model 2. 686, standard error of 10.4 again, minus 1.1, 0.52. This should have student-teacher ratio, minus 0.65 times the percent English language learners, with a standard error of 0.031. So now one thing I want to immediately point out that some people brought up on the last homework was that when you include a second variable in the model, or even more than a second variable, maybe 2 or 3 extra variables, the coefficient on the variable that was in the previous model changes. So the coefficient on student-teacher ratio went from negative 2.28 to negative 1.1. Is this a problem? No, this is not a problem. This is precisely why we want to include the extra variables in the model. Remember the story about omitted variable bias? Percent English language is left out of equation 1, meaning that it's an omitted variable that could be causing bias in our coefficient estimate. So if percent English language is correlated with student-teacher ratios, that would violate assumption 1, OLS assumption 1, meaning that the coefficient on student-teacher ratios in model 1, this coefficient of negative 2.28, is biased. We actually see this in practice here, that by adding percent English language learners to the model, equation 2, that the coefficient on student-teacher ratio declines in absolute value. So it goes closer to 0, meaning the effect size is diminished when we control for this additional variable. And we saw at the beginning of lecture note 6 that that's the case because because of the correlation structure between percent English language learners and student-teacher ratios and percent English language learners and test scores. Okay, so let's estimate some t-stats and some confidence intervals about these coefficients. Okay, so for our main hypothesis is going to be that student-teacher ratios have no effect on test scores. We're still concerned about that. We're hired by the school district, and they're still wanting to find out do smaller class sizes influence test scores. So our null hypothesis in both models models 1 and 2, null hypothesis in both models is H naught that beta 1 is equal to 0 versus beta 1 not equal to 0. Now, which one's beta 1? I should have written down the population model first, but beta 1 is the coefficient on student-teacher ratio. Yikes. So beta 1, it's the first variable in the model, so it's beta 1. Okay, so the confidence interval in the t-stat in the for the single regressor model is going to be as follows. So the t-stat in equation 1 is equal to beta hat 1 minus 0, because that's our null hypothesis. I should put a little 0 there, over the standard error of beta hat 1. Which is equal to negative 2.28 divided by 0.52, which gives us a t-stat of negative 4.38. So do we reject our null hypothesis in this case? Is the t-stat in absolute value greater than 1.96? Yes, it is. So we reject our null hypothesis. So in the single variable model, that says that student-teacher ratios have a significant association with test scores. We can't claim causality because we can't necessarily say that assumption number 1 holds, or all the OLS assumptions hold. How about a confidence interval? So 95% confidence interval is equal to beta hat 1 plus or minus 1.96 times the standard error of beta hat 1, which is equal to an interval of negative 3.299 and up to negative 1.23. So the question we should ask ourselves is, does 0 fall within this confidence interval? Does 0 fall within here? No. We should know that because we've also written down our t-stat. We've already rejected the null hypothesis with 95% confidence, so we know that 0 should not fall within the 95% confidence interval. But this does tell us the range of values that we cannot reject with 95% confidence. So let's do the same thing for the multiple regression. We're going to test the null hypothesis that beta 1 is equal to 0 in equation 2. Let's do that in green. So let's say this is model 1. Now let's do model 2 in green. All right. The t-stat for this is going to be this. We're going to do it the same way. The null hypothesis is still 0. T-stat's going to be beta hat 1 minus 0 over the standard error of beta hat 1, which in this case, let's go back up and see what it is. It's negative 1.1 divided by 0.52. That's our standard error. Let's make sure I wrote that down correctly. Yep, 0.52. So negative 1.1 over 0.52. So this turns out to be negative 2.54. So again, can we reject this null hypothesis? Is the t-stat greater in absolute value than 1.96? Yes, it is. So we can again reject our null hypothesis. So even when we include percent English language learners in the model, equation 2 here, we still can reject the null hypothesis, suggesting that there is a significant correlation between class sizes and test scores. The magnitude of that correlation has declined, going from model 1 to model 2, but the significance is still there. At least it's 95% significant. 5% significance, 95% confidence. So what's our confidence interval? Write that down. 95% confidence interval is equal to beta hat 1 plus or minus 1.96 times the standard error of beta hat 1, which in this case is equal to negative 1.95 up to negative 0.26. Okay, so those are the values that we can't reject with 95% confidence. Again, 0 does not fall within that range, so we reject 0. But this range has gotten smaller, and it's also decreased in magnitude relative to Model 1. So what can we learn? We learn that there's a robust relationship between student-teacher ratios and test scores. Even if we include percent English language learners in the model, that relationship between student-teacher ratios and test scores remains strong. At least we're 95% confident that we cannot reject the null hypothesis. We also learned that there's some omitted variable bias in equation 1 here. We learned that by including percent English language learners in the model, the coefficient beta 1 on student-teacher ratios declines in absolute value, and it gets closer to 0, so that the effect size is decreasing when we include that variable. That indicates there's some omitted variable bias in Model 1, so it's important to include percent English language learners in the model. It doesn't necessarily mean that equation 2 is free of omitted variable bias. There's probably something still left in the error term that's correlated with student-teacher ratios and percent English language learners that we're not including or not accounting for. So it's tough to argue that this is more than an association. It's tough to argue that we've achieved causality here. Okay, so next up we'll talk about tests of joint hypotheses, and I'll post that in a bit.